Hi again, students. This is our video on limits. This will be the final video for this week. I'm still in the church libraries. It's night now. These videos take a very long time. There's a lot of editing, practicing, scrapping of videos, redoing of videos, etc. So I hope you guys are making very good very good use of these videos. Alright, limits. I will not be doing any limit question because you guys have all the solutions for every question is asked in PDF through the email. But what is still confusing is that in all the different limits questions, it seems as though they take random or random paths to whatever answer they want to get, and on your own you would not have taken that path, right? So I'm going to show you all the answers, show you the solutions, and show you what's the logical thinking process needed to choose the correct paths. So let's go. Alright, so what I was saying is you have the solutions here. Now if you have a limit, we're looking at this question. If you have this limit here and you just have if when you plug in the value for x, it does not cause a discontinuity, like it does not cause, you don't see a 0 over 0 or anything like that, you can just plug in the x value and get the answer. Right, so that's why for this question you just plug in 2 and you will get 6 if you plug in 2 wherever you see x. So that's simple enough. Question number 2. If you plug 3 in here, then there is a problem. Is there a problem? No, it's still not a problem. Excuse me, 3 squared is 9, 9 minus 2 is 7. You have a number over a number, and that's 16 over 7. That's quite easy again. Here, we finally see a problem here, because we get 0 over 0 if we plug in the x. So when you have something like that, what is the logical thing to do? Use your calculator, right? Use a calculator so you will see what the answer is supposed to be. Now I did a video earlier on how to use a calculator properly, and so you can refer to the video for instructions with this. Alright, so remember, we can't plug in 1 because we can't plug in 1. So we have to plug in numbers very close to 1. So we'll do a test with 2 numbers, just one slightly above 1 and one slightly before 1. And if we get the same answer, we know the limit exists, and that's the answer we have to work towards, right? So what I will do, I hope you can see, it's dark now, right? So just below 1, I'm going to use 4 decimals. 0.9999, right? I just call this A, right? And 1.0001, let's call this B, right? So let's go. A square. Alright, A square minus 1 in brackets. We must put the brackets. A square minus 1 divided by 1 minus A, close bracket. You see they got negative 1.9999. So we can make a rough thing, so this could be approaching 2. Just want to do more values to see it clearly approaching 2, but again, it's just a random thing. So we tried A, let's try B now. Put B there. and then B there. Good. So for just both just above and just below, we see above and just below -2. So we know that this answer is going to be, should be -2. We actually know what answer we have to work towards. Right? So that's the first thing to think of. A warning. I just noticed this thing. When you're using your calculator to do this, some calculators do not handle these these letters properly. That's why I like to use Sharp. I think Sharp is the best for first years. Casio doesn't handle this thing properly sometimes, and someone let me hear this join us is not handling this thing properly either. Because if you use A, right, multiplied, or let's do A, we know A is 0.999, right? So if I do A plus 1, I get 1.9999, which is correct. However, if I recall A plus 1, why did I get 2.9999 this time instead of 1.999? If A is still 0.9999. If I do A plus 1, so I'll get 1.999. What the calculator did, when I called A, when I said plus, they turned A into answer. This answer being the last answer I just got. So like for instance, 6 times 6 is 36. 36 is the last answer I got. So if I do A plus 1, they turn the answer plus 1. So they add a 1. Instead of getting the 0.99 plus 1, I get the 36 plus 1. Now this is the error some calculators do that. Sharp does not do this. So just when you handle it, make sure that A doesn't ever turn to answer. If I recall, listen, if I do this and then I do this until it turns to answer, then I will have to just try a different way around. Alpha A or something, and then I see it would actually maintain now. Alpha A plus 1 or times 1. I know for sure. Yes, at all times. So please be very careful when using the letters. Alright? Okay, this video might be long. So we did a test and we see it's heading to -2. Alright. Logical thinking. Anytime you have this 0 over 0 scenario, the step you should always take, always see if you can divide, if you can factorize out x minus whatever is here, x minus 1 out of the top and the bottom, basically. If the limit as x approaches 3 is causing a problem, see if you can factorize out a x minus 3 on both at the top or the bottom. Let's just make the common. If you have whatever the value is, if the limit as x approaches -10 is what's causing the 0, then try to factor out x minus -10, or try to factor out x plus 10. So that is the logical step they did, right? They have this limit. You see, you do the calculate. You see that's supposed to be -2. So we know you're working towards 0 over 0. So you factor out x minus 1. You already know it. So that's what they did here. So that's how they get x minus 1 and x plus 1 there. Alright. Now the problem is you have a 1 minus x here and x minus 1 here. This is just a small trick people do. Well, in general, that you can do in maths. You can, instead of saying 5, you can express 5 as negative minus 5. I still didn't change anything. But you might want to do that to make a -5 common in both the numerator and the denominator. Alright? So, since they have a x minus 1 here, but a 1 minus x here, you can't cancel anything, but you know you want to cancel top and bottom. So you re-express x minus 1 as negative of 1 plus 1 minus x. Alright. Let me just show you why that makes sense. Alright, very quickly. What they had is x minus 1. Oops, sorry. Go x minus 1. The negative of that, right? We know x minus 1 is the same thing as negative of negative x minus 1. Then next to positive, right? But what is negative of this? It's same as negative of negative x plus 1, right? Which is the same as, oops, wow, which is the same as negative of 1 minus x. So just rearrange that. Don't worry, nothing else you see, right? So that's basically what it is. So you call x minus 1 negative of negative x minus 1. You didn't change anything. And then you just rewrote that as negative of negative x plus 1, which is still as negative of 1 minus x. Alright? So again, I'm showing the logical steps of it. So good. At this stage, you write this back as negative of 1 minus x, and the 1 minus x will cancel out with this 1 minus x, and the negative in front here will just go to this part here. So you have negative of x plus 1 remains. So that's how this turned to that. And when now you can plug in the value 1 without anything going to 0. No, not anything going to 0, without 0 over 0 or infinity over infinity. And you get negative of 1 plus 1, which is negative 2. Exactly the answer you wanted because you put that in your calculator. Those were the logical steps they took. Okay, example 2.2. Alright, what is that we have here? Oh, well, the limit, again, the first thing you check to see if when you just put in a value, there is no discontinuity, no 0 divided by 0 or infinity times infinity or 0 times infinity, none of those stuff. There's nothing there, so you just put it in and you have the fifth root of 8, and that's it. Okay. Number 2, which is this one. We see we have the limit of all that. So if we put in the 0, we see 0 over 0. Alright. So the first thing I said just now is to factor out an x. Well, actually the first thing I said is to see what the answer is supposed to be. Alright. So alright, let's see what the answer is supposed to be. Alright. When we know what the answer is supposed to be, we can actually, most time you have an idea of where to go. Alright. Oh, it's getting darker. So we choose a number just above 0 and just below 0. So let's choose 0.12341. Alright, let's use 3. Alright. And I will store this in A. Alright. And let me just do a negative of it. Right? Negative 0.1231, and then store that in B. Right? So A is that and B is that. Good. So we have the square root of open bracket A plus 2 close bracket minus root 2. You put all that in 2 very big brackets, insert, right, and you go back, divided by x, which is the A. The answer is that. Right? When I do B, put B in the place, B there, then I put B there, boom. So I see I get just about the same thing. Alright? And oh well, Many times, let me give you a tip with this. When you have something looking like this, try as much as possible to express it as a fraction. So it basically helps you to understand where you're going. And I'll show you that clearly in some other cases. The fraction totally helps you. And when you see something looking in these forms, square root 2 and root 3 and things like that, see if you can express your answer as something related to root 2. So alright, let's see what's root 2. Alright. Let's see if 1 over root 2. Okay, still, if we divide this by 2, oh, if we divide it by 2, then alright, it looks like that we had just now is the answer. So 1 divided by 2 root 2, so that's 0.5353. This we know where answer is going to be 1 divided by 2 root 2. Alright, so I said just now, if you have 0 over 0, the first step you should take is to factorize an x and then try to x minus whatever you have here, and just try to do some cancellation. Alright, so in this case we have to factorize out x. The only way we can, you see, the x, there's no way we can factorize x easy in this case, because there's a big square root sign over the x plus 2, right? So the only way we can factorize is if we multiply the x plus 2 by x plus 2, right? So basically, and there is a logical step, so that's why they multiply this whole thing by the same thing here, the conjugate of it. And of course, if we do to the top, we multiply to the bottom, so you multiply the top and the bottom by x plus 2 plus root 2. Right? I'm getting really tired. And when you work this out, you just get that. And as I said earlier, why does it look so confusing out of there? Anyway, as I said earlier, what you do is factor out an x, right? Alright, did I skip any steps? I see that. Oh, wow, I can't even see this. Alright, x is there, so 2 minus 2, very tired. 2 minus 2 is 0, and x goes up to the x, get left back with that. And left back with that, then you plug in the 0, and you get 1 over 2 root 2. So yes, they did a completely different thing in this one from the last one, but all it is something completely different, was still following the exact logics. You know, you have to just factorize out the x, so you had to get the x out from under here. That's why they had to multiply. Just multiply by the conjugate. This multiply by this to get the x from out of this thing here. This is how they got this x plus 2 by itself. The factor the x and this. So again, different path, but by using the same logical steps. It's already 18 minutes. Alright, next question. Sine inverse of x plus 1 over 2. If we put 0 in there right away, we get sine inverse of 0, and let's see what that will give us. Wow, sine inverse of 0 is equal to 0. Following the logical steps. Oh man, really, I'm getting tired. We have sine inverse of x plus 1. X goes to 0, right? So this is just sine inverse of a half, and it's just there's nothing else we had to do. As I said, we only do the next step when we see something looking like 0 over 0 or 0 times infinity or something you can't work out. If you plug this in, 0 here, and works it right away, you just get the answer. Alright, focus. Alright. Next question. We have x cut x. So let us do this. Alright, you don't know what's cut. Cut is 1 over tan. Alright? So if we plug x, the 0 into here, we will get this. Because we get 0 and 1 over 0, which is infinity. So 0 times infinity. And and that is a case when you know, okay, this can't work out. Let's see what our answer is supposed to be. And then let's see how we will logically get this answer. So we already have a and b stored as just above and just below 0. So let's go. A I killed it. A multiplied by cut, which is 1 over tan of A. Close the bracket, and I get something close to 1. And then I do alpha b, and it equals something close to 1 again. So I know this answer is supposed to be 1. So I practically know where I'm heading to. So I will keep readjusting the equation until I get 1. I will not give up until I get 1. So what I said is you must, when you have it here, forget what you say, when you have it here, factor out an x. But this time we see that okay, it's not like that because it's not a simple numerator denominator something. So you step out of that logic and you go to the second step. The second step, well, in general, from since secondary school, you're accustomed working with cos and sine, right? So if you see a tan turns into a cos and sine, you can basically keep using the rule all the time. Tan of x is equal to sine x divided by cos x. That's in general. If you see a cut, turn it into 1 over tan. Oh, try to turn everything into cos and sine. That helps you a lot, right? So that's why. I'll give you some other rules there. Logical steps, right? The first one is if you see 0 over 0 factors of x minus the thing of cos is 0. And the second step, the second logical thing, express all trigs as in terms of sines and cosines. So that's why they re-express cot. Cot is 1 over tan. So if tan is sine x over cos x, and you have 1 over tan, so you have 1 over sine x over cos x. That's why you have cos x over sine x. So I did the second logical thing, expressed it in cos and sine alone. But when I plug in here into here, I still get 0 over 0 because x is still 0 times cos 0. The 0 times 1 over 0. 0 over 0 is still. So alright, back to square one. Could I now factor out an x? How could I factor out an x? There's no way you can factor. When you have a cos here, a cos of something or sine of something, you can't ever factor anything out of this cos or the sine. You can't factor anything out of the trig function. So okay, so what do? We're stuck. But alright, we know that 1 is the answer. We see x, cos x, and sine x. We know the answer is 1. Now we go to the third logical way to think of logical way of thinking to solve limits, or maybe the fourth. Can't remember how much I call it. What you do now is see if you can replace one of the trigs with a different trig, which would stop this, which would stop this situation from happening, or yeah, That's why sometimes you will see Miss make a trigonometry substitution. You might know why did she even make the substitution? Because you remember something 0 over 0. So you want to say, instead of saying sine x, if I know that sine x could be something else, you should write the something else, right? So you either you re-express sine or cos as something else, or you use a standard trig limit. So either re-express or use a standard trig limit. Um, Generally, the only time you would re-express is if you see something in the form of something looking like sine A minus sine B. Then you re-express that, or cos A minus cos B. If it's a single thing, most times not re-expression, it's just using a trig limit by definition, right? So if you use this, right, looking at that, and you know you have to use trig limits. You can write down all the trig limits you know, which is, there are 3 of them. It's already evening. I guess I will use tutorials this week to prove the 3 trig limits, which Miss did say is coming in test, right? The trust tree. Anyway, I'll do that during this week. But one you're supposed to know is sine x over x is equal to 1 as x goes to 0, right? So see how you can use that. And from logical thinking, you know you want to head to 1. You know if you put cos of 0 in 0 here, it's a 1 you're going to. This cos 0 is 1. And then you see x sine x. But you know as sine x over x, as x goes to 0, the answer is 1. So you can technically, if you can rearrange this to make it look like sine x over x, you actually get 1. And you actually know what 1 is the answer. Right? So what they did is put 0 over alright, yes, this is exactly what I'm saying. Alright, the limit of sine x over x as x approaches 0 is 1, because sine x and x would always have a ratio of 1. So technically it would not matter if x is at the top or the bottom. Alright? X over sine x as x goes to 0 is 1, and sine x over x as x goes to 0 is also 1. Right? So you could have still forced a rearrangement, but they still got the same thing. But they didn't even go through all that. They just split it like this and got the 1. Alright? It's already almost half. Or remember, yes, I'm stretching these videos out because I just want to carry you through the logical steps. So when you look, it might take about more than an hour and all. But I just want you to get the thinking behind how they got the answers. Alright, good. So the next is this. Prove. What was this? What they asked to prove? They didn't ask the limit. Alright, exercise. Alright, just now. Let me look for the paper. Exercise 2.5. Oh, so this is the question. Oh, alright. So, alright, when you have something here like this, in tutorials we show that as x goes to 0, you get cos, as x goes to 0 is 1 over 0, which is infinity, so you get cos of infinity, right? And cos of infinity can never ever be worked out, because as x approaches infinity with the cosine function or the sine function, the function is not approaching any particular value. It just fluctuates between -1 and 1. So in general, anytime anytime you have something as simple as this, and you just have a cos of infinity, you start with the fact that how can I that alright oh alright you start with the fact that cos of x would always be cos of x would always go between -1. Well, oh, what am I doing? Tired. Then 1 less than equal to cos of x. It will always go between that and that. Alright, now what we always do is turn this into what you have here, and then evaluate the limits of on this side and this side. Right, so alright, how can we turn that into that? Alright, this is as x goes to infinity. Alright, we have something unusual here because we see we have cos of 1 over x. So how can we get the cos of 1 over x? There's no way we could turn that x into 1 over x by doing any manipulation throughout. So okay, what we do is, oh, it's simple. If you're gonna keep this form, right, cos of x as x goes to infinity is this. Then when you turn this middle part into the function you have, then you have to evaluate this side and this side as x goes to infinity. And next way you can rewrite this it's like this, right? But if you're gonna do this, the only way this can still go to infinity. Whoa, I'm getting really tired. The only way this can still go to infinity is if x goes to 0. So this and this is the same thing, except this is that x goes to infinity. So you got this for this side and this side, and it says x goes to 0. So that's what he did. So let me show you the steps. So you do this, you wanna get that. So you just multiply every side by x squared. So you just simply do x squared is negative x squared, you will get, right, x squared. And we said limit as x goes to 0 to catch infinity, right? So the limit of this as x goes to 0, it's just 0, right? So it's 0 on that side, and this side x goes to 0 is 0 also, so the answer is just 0. And that's what basically they did. I'm very tired. I don't know if I'll continue this much longer. I think I'll do the rest in tutorials. Been standing for maybe 5 hours or 6. Alright, let me look for some. I'm not gonna go through all anymore. I'm just gonna look for some strange looking ones. And let me see, 2.6. Alright, this one. Alright, what's the original question? The original question is limit f x goes to 0. Alright, if you look at this, right, what they did is just, remember when I showed you A and B, right, in the calculator, I had A as a number just above 1, and B as a number just below 1. So the 1. Just above and just below is 0. That means I really have to stop. Just above and just below is 0. So the one just above is called 0 plus, and the one just below is called 0 minus. So when they did that test, they did not get the same. Remember, I kept doing both tests and kept getting the same answers. Why I concluded that this answer we're supposed to work towards. If you do that test in this case, you get 2 different answers. So you see the limit does not exist. That is the end of that right there. Oh, example 2.7. Limit as x goes to 0. We have the same thing like before. I'm not gonna go through that. That's the same, and then you multiply the conjugate because you wanna factor that out. Alright. See, with this, again, this one was done before also. If you plug in 1 here, you get 0 over 0. So you try to factor out the x minus 1. And that's why they did this. They factored x minus 1 from here, the top and the bottom. See, it was a completely logical step. Oh, in case you might know how to factor out, just divide this by x minus 1. And with the answer you get, put x minus 1 and you just, and you get this and 3/4. Oh, of course I actually skipped a step. When you're here, what I said is when you get 0 over 0, put in just above 1 and just below 1, and you would have gotten 3/4. And then you work towards 3/4. Right? So this one, what they did is rule number 2, as I told you guys, they did not use tan, they used sine over cos x. And when you flip this, the signs will simply cancel and you just get that. Oh, remember the second step, I skip that again. When you have 0 over 0, put in this in there.